In the last video, we considered stochastic integrals, and along the line, we saw the Itô integral, which I think is the most important of the stochastic integral. So let's go ahead and look at Itô integral in some depth. Now, um, the motivation for Itô integral is that in classic calculus, integrals like integral from 0 to t of f of t dt require smooth functions f of t, right? However, in stochastic processes such as Brownian motion w sub t, which we talked about in the last video also, parts are nowhere differentiable. So the w dt does not ever exist. Then variance grows with time, and classical calculus fails in that context. In that case, we therefore define a new object. Instead of integral from 0 to t of f of t dt, we now have integral from 0 to t of x sub t dwt, where x sub t now, or if you like, you can also call it x of t. So the whole thing now is called the Itô integral, right? And of course, to put that in context, we also need to remind ourselves of Brownian motion, which is the most important stochastic process. So a process W sub t is Brownian motion if W of 0 is 0, that's the initial condition. At time 0, the motion is 0. Then it has independent increments, and Wt minus Ws, which we can also say W of t minus W of s, is normally distributed within 0 and time, since it grows with time, right? So what we have is just the variance is simply be the since variance grows with time, that is, so it means the variance will just be the difference in time steps. Then it has continuous parts. And then the key identity for Brownian motion is that the Wt all squared is simply dt. And this is fundamental in Itô calculus. We saw that in the last video. So here we are just trying to dig deeper. So definition of Itô integral now. So the Itô integral is defined as integral from 0 to t x sub t dwt as the limit of sums, summation from I equals 0 to n minus 1, x t sub I into wt sub I plus 1 minus t minus wt sub I. And it is important that the integrand is evaluated at the left point, the left endpoint ti, right? And then this distinguishes Itô from other stochastic integrals. Now, we go on and talk about the properties of Itô integral. So, first of all, there's linearity. Linearity means that if you for instance, the integral of a sum is equal to the sum of the integral. So if you have the integral of a x sub t plus b y sub t dwt, it is as good as saying a times the integral of x sub t dwt plus b multiplied by the integral of w sub t dwt. And then the mean, of course, is always 0. So the expected value of integral from 0 to t of x of t dwt is always 0. And then we have Itô isometry, which we also saw in the last video, that the expected value of the integral of the square of the Itô integral is simply the expected value of the integral from 0 to t of xt squared dt. And that makes sense because x of t squared is x of t squared. The wt squared is equal to dt because we have this memory that the wt squared is equal to dt. So that's why this isometric can work. That x of t dwt all squared is exactly the same thing as integral from 0 to t x t squared dt, like that. So we can take an example. So you want to compute integral from 0 to t 1 dwt. Of course, the solution is, because this is just one, right? So integral, that's just like integrating the wt, which is wt from 0 to t. So if you have wt minus w0, and w0 is 0, so the answer is wt when you are just integrating the wt. In example 2, if you want to compute integral from 0 to t of wt dwt, so the result is integral from 0 to t wt dwt equals 1 over 2 wt squared minus t. Of course, we got all of this idea from the Itô lemma in the last video. So because the first thing you take is, if you want to do this, you first of all leave it alone and do f of w to be equal to w squared, and then you now so you now use Itô lemma to form it, and then at the end of the day you end up getting half wt squared minus wt, like that. So, and then we have the derivation of Itô lemma. So look at the Itô lemma here. So what we have got here now is what we want to now derive here, just like we did in the last video, except that the notation is a bit different, but it's functionally the same thing. So if you let f of wt be wt squared, right? So that's how we end up getting this place now. So if f of wt is wt squared, Itô lemma gives that the wt squared, right, will be 2 So, you differentiate this 2wt dwt plus dt at the end of the day because you're going to have wt squared all like there. So you have dt. So in that case now, if you need this expression, which is what is being integrated here. So to isolate this expression, you have to divide through by 2. So you then have wt dwt equals half half d sub t squared minus half dt. So if you then integral from 0 to t w sub t dwt, that will simply be, of course, this d will disappear, and then when you integrate dt, you get t, and then if you evaluate, you get t minus 0. So you have half into wt squared minus t. So that's how this actually came about like that. And then, of course, we can simulate the Ito integral simulation. So if you take t to be 1 and you take 1000 steps and you take dt to be t over n, so you have Brownian increments and it ends up giving you 0.5359 and this is 0.5240. Pretty close. This is the Ito approximation and then this is the theoretical value. So they are very close. So that means that the Ito approximation works perfectly. And then we have Ito versus classical calculus. So talking about the feature, right? For talking about smooth parts, classical calculus has smooth parts. So because you have continuous functions, but for Ito, they are stochastic because of randomness. The chain rule is standard in classical calculus, whereas it has to be modified in Ito calculus, right? Then the W squared in classical calculus is 0, and then but in Ito it is dt. Then integral, in classical, it's Riemann integral, and Ito is Ito integral, like that. And then we refresh our memories about the Ito's lemma. So, in fact, we're still going to look at Ito's lemma in a separate video. So, if dx sub t is mu dt plus sigma dwt, now all these ones have meanings, especially when you get into like finance applications. We're going to see that also. Then for a function f of x sub t, df now is f prime x sub t dxt plus half f prime prime xt sigma squared t. So that's like so uh for any given function f, which is a function of x sub t, you get this now for that. So, and of course you can always fix, if this is the xt, you can fix the xt here and then evaluate that. That's why this ends up being sigma squared dt. So if you put that into this, okay. So with that in place now, we then have this. I'm trying to think of expanding that fully. Trying to think about this. Okay, yeah, let's just keep going. So, example, let f of x be x squared, then we have df now. So, if our f of x now is x squared, so f prime of x of t, that's differentiate this with respect to t. There's no t there, so it is going to go to 0. So, 0 times this part. Oh, okay, no. Yeah, this fine. This actually work. This works. So, differentiate this with respect to x. So, you have uh 2x dxt. So that'll be 2xt dxt. Plus, when you come here now, if you differentiate f prime of xt, so that means if you differentiate this first time, you get 2x. Differentiate the second time, you get 2. So, that's half times 2, right? Half times 2, which is going to cancel out, and you just have sigma squared dt. That's why you have this here. So df is 2xt dxt plus sigma squared dt. So in summary, we see that Ito integral handles non-smooth stochastic paths, and then it uses left endpoint evaluation, that's TI, and then the mean is 0, and it follows Ito isometry. Then it requires Ito's lemma instead of classical calculus. So um, we have the practice problems now. Mm, Okay, I'm going to solve the first 5 of these problems, and then I'll leave you to do the hard task of the rest. Of course, you can easily use the all the expressions, all the ones I've talked about before. So you want to compute integral from 0 to t, 1 dt. dwt is easy, we go for it. You have t dwt, we go for it. You have w sub t dwt, and then you have wt squared dwt, and then there's wt dwt. Is this a that thing? Oh, the expected value of this now. Okay, so I'm doing this top first five, but don't forget you can so also try your hands on the rest. So this you have 6 to 9 here, for instance. Here you have 6 to 9, and then we have 10 to 30, 10 to 13. You have 10 to 13 here, and then we have 14 to 17, and then we have 18 to 20. So I'll go and solve the first five. So I'll just breeze through that as fast as I can. So for question one now, we need to compute question one, compute. I think it's been done there, but I want to just try to explain as much as possible here. Compute integral from 0 to t, 1 dwt, dw sub t now. Okay, so we know that will simply be, um, so we have integral from 0 to t, 1 dw sub t, and that is equal to integral from 0 to t dw sub t. So an integral d anything, the d integral just cancels d. That's the usual thing that happens when if that's all you have there. So that would just be w sub t, all right, from 0 to t. That means we have w sub t minus w sub 0. Okay, and we know that w sub 0 is equal to 0 in a Brownian motion in a stochastic process. So that means that integral from 0 to t of 1 dw sub t is simply w sub big T, and that's what we have there. Okay, so I move over to the next question, two, which requires us to compute integral from 0 to t of t w sub t, like that. So to do that, we say that of course this is a deterministic integrand, is a deterministic integrand with the following properties, Okay, so the first one is the mean, right? We have the mean. The mean is such that the expected value of integral from 0 to t, t dw sub t is equal to 0. That's the expected value right there. That's the first one. And then the second one is the variance. So we get the variance using Itô symmetry. Variance using the Itô symmetry, using the Itô isometry rather. Itô isometry. Okay. So that means we have the expected value from Itô isometry. That's the expected value of integral from 0 to t the w sub t all squared. Of course, that's clearly going to just be integral, integral from 0 to t of, square this. That's t squared the w sub t all squared, like this. So, and with this now we can just continue, and we have integral from 0 to t of t squared. The wt squared is simply dt, and then we can just integrate and keep moving. So if you integrate this now, we have integrate t squared, you have t cubed over 3 from 0 to t. So that means we have 1 over 3 into t cubed from 0 to t. So that means that's 1 over 3 into t raised to power 3 minus t minus 0 raised to power 3. When you take this t up there, and t raised to power 3, 0 raised to power 3, like that. So that means we have 1 over 3 t raised to power 3. This is 0, so it goes. So we have this expression right here. So with that in place, then we can say that uh we can then say so integral from 0 to t of t dw sub t is normally distributed with mean 0 and variance Of course, this is the same thing as t cube over 3 for sure. So t cube over 3. So that's variance t cube over 3. And that's how that goes. So that's question 2. So I move off to question 3 now. So question 3, we want to compute we want to compute integral from 0 to t, w sub t, dw sub t. That's question 3. So how do we go about that? We know, so we use Ito's lemma on f of w sub t equals wt squared. We need wt, dwt. So if you use Ito's lemma on this is what is going to happen. So we know, using Ito's lemma, right? We know that this is going to be um um okay. Yeah, I think I need to go and bring Ito's lemma so we can follow it the way it is. We saw Ito's lemma somewhere. Where is it now? Okay, Ito's lemma. Ito's lemma. Yes. No, it's not this now. It's given concisely somewhere. It's given concisely somewhere. There's a formula we saw that was yeah, this is it. Very good. So this is it right here. So we have, okay, I think I need to snip that, and so I can just apply it. So I take this, then I just come snip this. Uh, so this is like summary of the Ito's lemma. So I just come, okay, I guess I need to do that again. Guess I need to do that again. Okay, yeah, I can just copy. No, I was saving instead of copying. Okay, I copy, yeah, then I bring it here. So yes. So we have this now. So if you use, this is f of wt now. So in this case now, the f will have to be f prime of x of t. So in this case now, what we have is w of t. So I can actually rewrite this to say this is df equals f prime of f prime w sub t, then dw sub t plus half f prime prime w sub t sigma squared dt, right? So with that in place now, because we have our function is of wt squared. So in this case now, we then have so df is equal to f prime w of t. That means differentiating this, which is 2 w sub t. Then we have dw sub t right here, okay, plus half. So if you differentiate f prime w sub t of already is 2w sub t. So f prime prime w sub t would just be 2 in short, to just be 2, which is now constant. So that is half times 2, right? Multiplied by sigma squared dt. And then that's what we have there. So we then have df to be 2 w sub t, dw sub t, 2 cancels out, plus sigma squared dt. So that's the df we have now. That's not the end, right? Because what we want to integrate at the end of the day is sub t, dw sub t. So this is what we are looking for, actually. This is what we are looking for. So if you can isolate that, it means we have, of course, it means we have df minus sigma squared dt. And that is 2 wt dwt. So we can then rewrite that as 2 wt dwt, and that is df minus sigma squared dt. But don't forget, f is already given as wt squared, right? So that means we have 2w sub t dw sub t, then df is w sub t squared, right, minus sigma squared dt. So, and then we can take away this to divide both through by 2. So with that, we have w sub t, d w sub t equals So divide 3 by 2, that's half, right? That's half d into w sub t all squared minus half sigma squared dt. Okay, half sigma squared dt. Now, if that is the case, then we can integrate. So this is another milestone in this process. So we can then integrate. So integrating from 0 to t. So we have integral from 0 to t, w sub t, dw sub t. That's the original problem, right? That's the original problem we're solving. Integral from 0 to t, w sub t, dw sub t. That's the original issue. So we have that now, and that is equal to of course, half can come as half integral from 0 to t, w sub t squared, then minus half sigma squared integral from 0 to t dt. Okay, so we can tidy up all of this. This is half. Integrate the d of anything. Integral cancels d. So that's the idea. So we then have w sub t squared from 0 to t minus half sigma squared, you know, integral of dt, that's simply t from 0 to t like that. So we can tidy things up again. We have half. Okay, I guess I need to switch it up here. So I have half into w. If you put big T, that's wt squared minus w0 squared, you know. That's when you put the limit, that's w0 squared minus half sigma squared into t minus 0. Okay, so this is half into wt squared minus w0 squared is 0, right? Uh, okay, recall, right? So recall, we need to recall that w0 is equal to 0. Okay, if that is the case now, so that means this whole thing is half into um, wt squared minus 0, okay, minus half sigma squared into t 0, uh okay, yeah, t minus 0. Let me still keep that level. So we have half wt squared, 0 is gone, minus half sigma squared t, and 0 is also gone. Okay, um sigma squared. So this is the expression right here, sigma squared. Why do we still have sigma squared showing up? I'm wondering, why do we still have sigma squared showing up? Shouldn't it have gone away? So why do we still have sigma squared? Because in the final analysis, sigma squared shouldn't be there. Only dt is showing. Okay. Uh, okay. This goes like that, right? Mm, so this is basically half wt squared and a sigma squared t. So I so this well, if sigma squared is 1, right? So it disappears, but I'll just leave it like this. So, but if you I know this sigma squared should not be here, but from Ito's lemma, we have sigma squared appearing. Um Probably this should just have been the W or something. So, but that's fine. So I just moved to question. Okay, well, let me leave the other questions, right? I was thinking I would do question 4 and 5, but yeah, I'll just leave that alone for so that you can try your hands on the rest. So let me just leave it here and move to round off. Okay, so don't forget, look at the problems again and try your hands on them. So or I think we did something close to that, because here from Ito's lemma, dt, we only have dt here. So The sigma, where did the sigma go to? Ito's lemma. Okay, this is the Ito's lemma. But even the lemma itself, yeah, we have sigma squared showing here for sure. Mm, okay, I mean that's fine. So probably sigma is if sigma is one, it goes to sigma squared goes to one, so it's fine. So we have questions 1 to 4, question 5 to 8, question 9 to 12, question 13 to 16, question 17 to 20. Try your hands on them and let's see how helpful this has been for you. Let me know what else you might want me to try out again. Don't forget to subscribe if you haven't done that already. If you have subscribed, I thank you so much for doing that. Beyond that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first or seeing some videos exclusively, uh, you know, as a member of the channel. You can request for PDF copies of my notes. We can hang out together to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, share so that other people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.